Hello. In this video, we're going to talk about polyatomic molecules. Um, I'm sure you've figured out by now that when we get into the domain of reality, things are a lot more complicated than the simple theories that we had for the hydrogenic atom and the diatomic molecule. And polyatomic molecules are even more complex, and the details of their molecular structure are really beyond um, what we'll consider in this course. There are just a few things that we need to be aware of. Again, you can go to the NIST database and learn things about their structure and the wonderful series by Hertzberg. Um, so, um, so um, for a body made up of n atoms, there are 3n degrees of freedom. This is simply comes from dynamics. Um, if you consider the center of mass, the whole body of the n atoms can translate, and it can take up 3 degrees of freedom of the motion of the 3n degrees of freedom of motion. Um, if the if the body, and I guess I should say molecule because that's the body we're talking about, if the molecule is linear, that is, if the atoms, all the atoms in the molecule are in a straight line, then there are 2 degrees of rotational freedom, just like the diatomic molecule. But for a general nonlinear molecule, there are 3 degrees of rotational freedom. And so then vibration takes up either 3n minus 5 or 3n minus 6 degrees of motion. So here's a couple of examples of 2 polyatomic molecules, simple ones, albeit. The first is CO2. It's a linear molecule, so it has 2 degrees of rotational motion. And the other is methane, or CH4. It is nonlinear and has 3 independent axes of rotation. So the vibrational modes, again, it depends on the configuration. CO2 is linear, so it has 4 modes of vibration. And they are shown here. There's a symmetric stretch, a so-called asymmetric stretch, and bending in 2 planes. And then a nonlinear triatomic molecule, H2O, has 3 modes of vibration, and it can be what's often referred to as a breathing mode, where all three atoms sort of go out and in together in unison. And then these other 2 modes that are illustrated. Um, So the electronic structure of the molecule is determined by quantum mechanics, just like in pure atoms. The electrons from the atoms form orbitals, and these combine when making a molecule into structures that are somewhat related to the atomic orbitals. And I just list the second row from carbon to neon, carbon, nitrogen, oxygen, fluorine, neon, and it gives the description of the orbitals of the shell and subshell. And if the orbital is a 2s orbital, then it's going to be isotropic, symmetric, more or less spherically symmetric if it's an atom, and if it's a p orbital, then it's going to have this lobed shape. And these play an important role in how molecules form and how they react, chemically react. Just a reminder from your first chemistry class, there are 2 types of chemical bonds: ionic, and that's where the charge on the atoms is mostly localized on the atom, and so that you have a negative portion and a positive portion of the molecule, and they're just held together by the electrostatic force between those. And then there are covalent bonds, which is normally the case. Most molecules are bonded covalently, and that's where the electrons orbits or electron charge distributions overlap, and that's what holds hydrocarbon molecules together. So a single bond involves 2 electrons, 1 from each atom. A double bond, 4 electrons, 2 from each atom, and a triple bond, 6 electrons, 3 from each atom. Just a little bit more about the chemistry of compounds. Compounds are classified in a variety of ways. These are normal ways to classify hydrides, oxides, halides, organic versus inorganic, ionic, and organometallic. We'll be mainly concerned with organic molecules, so it's worthwhile noting a few things about organic molecules. And one is the octet rule. If you look at the row of the second row of the periodic table, all of those atoms have a principal quantum number of 2, and as a result, if the subshells are filled, there will be 8 electrons around the atom, and that's neon. It's on the right side of the periodic chart. On the other hand, if there's only 1 electron in the outermost shell, in the n=2 shell, then you have lithium, which has this 1 electron. And the number of electrons determine how molecules are likely to react. Now, in my work, I'm interested mainly in hydrocarbons, which means I have hydrogen, which has 1 electron, and carbon, which has 4. Carbon, because it has 4, is open to forming covalent bonds, 4 covalent bonds with other atoms. And so, for example, methane, CH4, what you have done is form 4 covalent bonds, single covalent bonds with 4 hydrogens, and so on. Organic chemists know this, and they don't even draw hydrogens on their models. This is an example. First, some nomenclature. In organic chemistry, alkanes are single-bonded hydrocarbons, alkenes are double-bonded carbons, and alkynes are triple-bonded, and then arenes are ring compounds. So an example of each of these here, we have ethane, ethene, ethyne, or also known as acetylene, and ethene is often called ethylene. So ethane has a single covalent bond, ethene a double, and ethyne or acetylene a triple. And as I say, an organic chemist doesn't draw the hydrogens, and the reason is he or she knows the octet rule. So since carbon likes to form 4 bonds, with ethane we know there's going to be 3 hydrogens on each carbon. So ethane would be C2H6. Ethene, or ethylene, has a double bond, and therefore each of the carbons is capable of forming 2 more bonds. And so it would have 2 hydrogens on each end, so it would be C2H4. And then acetylene has a triple bond, and so there's only 1 possibility left for each of the carbons, and so if they're replaced by hydrogens, it would be C2H2. And then the bottom row of the chart shows benzene, and it shows it in various visualizations. So it turns out that benzene, which is C6H6, it's a little bit confusing. So it is commonly drawn as the second diagram in the row. That is a hexagon with 3 double lines indicating 3 double bonds and 3 single bonds. But that is not correct. In fact, benzene is what's called a resonantly stabilized molecule. The fact is that the extra electrons that are available are shared among all of the carbons. So sometimes benzene is written in the 3rd form in that line with just a circle. I think most organic chemists would draw it as the 2nd form, but for your sake, I've drawn it as the 1st form, showing the 6 hydrogens. And then you can also visualize a molecule by showing the iso surfaces of the electron density, and that's what that fourth image is, and we'll say a bit more about that later. So here are some examples. If you go onto the NIST database, you'll find that you can download what's called a mole file, which is a structure file that can be used in various molecular visualization programs, and here are just 5 examples. Benzene, which I showed you before. These are what are called ball and stick visualizations. So the atom is shown as a ball and the bond as a stick. It doesn't really tell you what kind of bond it is, whether it's a single, double, or triple, etc. But anyway, lots of different possibilities. And so this diagram shows that. So if you start out, if you look on the right-hand side in the box, and up near the top, there's 2 carbons, and suppose they're double bonded, and if the R's on that diagram were H's, that would be C2H4 or ethylene or ethene. But what the R's represent is the fact that you don't have to bond just a hydrogen to those carbons. You can bond anything else that can form a bond, and there are an enormous variety of so-called functional groups in organic chemistry, and some of them are shown here. And for this reason, really an unlimited range of compounds can be formed, and that's a good thing because we wouldn't be here if that wasn't the case. We wouldn't have DNA, we wouldn't have RNA, and so on. And here's an example of a bit more complicated molecule here. This is cellulose. Cellulose is a polymer of glucose, and the polymers are linked through an oxygen atom, as shown. And so just to reiterate, you can make a lot of different kinds of molecules, and we'll talk about some of them as we move on. So that's it for this video. Thanks for listening. Have a great day.